Hey everyone, happy Saturday afternoon. I hope your weekend is off to a good start. Let's just wait one more minute. We got a couple more people registered that are actually here, so I want to give them a chance to arrive. So just sit tight for one more second and then we'll get going. I'm going to go ahead and share my screen with you while we wait. There we go. So now you should be able to see my screen and then me down in the bottom. For those of you that are here right now, how many of you have covered optimization in class? Let me know in the chat feature if you've covered optimization yet. Okay, awesome, Stephen. So is your hope today, Stephen, to just kind of get some extra practice and review, or are you looking to try to get something else out of it? Awesome. Yeah, practice, practice, practice. I always tell my students the best way to study math is to do it, which means you have to practice it. All right, let's go ahead and get started. Okay, CJ, you covered it briefly, so hopefully this will help you get a little bit of a better grasp on it as well. Maybe we'll go more into depth than you did in class. Okay, but you'll have a good place to start, hopefully. Let's go ahead and get the stream started. Hopefully we'll have a couple more people trickle in as we go. My name's Suzanne Farrellock, and today's stream is going to cover optimization. Oops, I don't want the pen just yet. There we go. Don't forget to follow Fiveable on Twitter, Instagram, and YouTube so you stay up to date on all the latest streams and you can share them with your friend as well. So in this particular stream, we're talking about optimization, okay? We got to talk about what is optimization. And then we're going to discuss some general procedures for solving optimization problems, and then we'll get into the actual practice of it. So optimization, when we just kind of think of it as a big umbrella topic, is the study of how to do something in the best possible way. Now, if we want to do something in the best possible way, best can mean different things in the context of different problems. It might be the fastest, the biggest, the shortest, the most profitable. So you really have to take the word best in context of whatever problem it is that we're looking at. For example, businesses, they're going to want to minimize cost, but they're going to want to maximize profits. A traveler might want to minimize travel time. But again, big picture here, what we're looking at is making something the best possible. And when we do that, we are really going to be solving max and min application problems. A couple other comments I want to make here on this particular slide. Okay. When we talk about words like fastest, biggest, shortest, most profitable, these are going to be important types of keywords. And when we get to our practice problems, these are the kinds of keywords that we're looking for that cue us in onto the fact that, oh, this is an optimization problem. I need to find my critical points, figure out where the max is or the min is, okay? The other thing that I want to mention is if you're somebody that maybe wants some extra practice or some more insight on finding max and min, I did a stream, I think it was last week, maybe the week before, on increasing and decreasing. So that's something that you can go back and rewatch if you need a little extra practice with that. Any questions on just in general what optimization is? No? All right. So let's talk about our strategy for solving optimization problems. Very first thing is we need to actually understand the problem. We need to read the problem carefully, and we want to make sure that we know what quantity it is that we're trying to optimize. So that's going to be an important part when we read the problem, is we really want to make sure that we know what quantity is to be optimized. Okay. After that, I think the next best thing to do is to draw a diagram. So as we draw this picture, we're going to get a better feeling of what is happening, and it's also going to help us start to identify any given and required quantities that we need on our picture. And that will lead us into being able to label our picture by assigning variables and figure out which quantities are changing. So after we draw that diagram, we're going to also figure out how to introduce our variables. So those two kind of go hand in hand because one leads to the other. Then we get to write our equation. Now, this goes back to understanding the problem, making sure you know what quantity it is that needs to be optimized. We want to try to write a formula for the function that is going to be optimized in terms of the other variables we've just identified. Now, sometimes we're going to find it might just be one variable, but other times we might have a couple variables we're dealing with. And in that case, we want to use whatever other information they give us to figure out some relationships so that we can eliminate all but one variable. So our goal here is to get a formula in terms of one variable here. Okay. Then we're going to find the max and min. So again, with optimization, where we're looking for the best, sometimes the best might be a maximum, sometimes the best might be a minimum. It's all just going to depend on the context of the problem. When we find the max and min, though, what we're really doing is we're finding the critical points, and then we're going to figure out where our function's increasing, decreasing to decide if we have maximums or minimums. Now, also keep in mind, because we're looking at problems that have context, scenarios, application problems, sometimes we might also be restrained to certain values we can use. Those might impact some endpoints, or sometimes the endpoints might even be given. So we want to keep that in mind in addition to those critical points. Give me a thumbs up in the chat if you're with me so far. Type out any questions if you have them. I'll wait for those responses before we jump into actually looking at some examples now. Okay, awesome. Let's see what we got here. All right, so here is our first example. Our first example says a rectangular play yard is to be constructed along the side of a house by erecting a fence on 3 sides. And we're going to use the house wall as the 4th wall. Find the dimensions of the play yard of maximum area if 20 meters of fencing is available for the project. So take a couple seconds to try to kind of read through that on your own, digest it, and then let me know in the chat what it is that we are trying to optimize in this particular problem. What is the thing that we're trying to optimize? Yeah, exactly, Stephen. And the key here is that we are trying to maximize area, so it's the area that we're optimizing. Okay, so let's, yeah, good Sherilyn, good CJ, awesome. So let's draw a picture of what's happening here. We've got a house, and we are looking to fence in a certain area in our backyard for our play yard. Okay, so this will be my play yard in here. My art skills leave a little bit something to be desired. What are some other pieces of information we have from this problem that we're going to want to start putting into our diagram and thinking about variable-wise? Now, Stephen already alluded to it because he told us that we have 20 meters of fence that's available for the project. Label the left and right fence with X, okay? And the top of the fence with Y, and make an equation of perimeter. That sounds great. So think about what's happening here. If I need 20 meters of fence, that means that my perimeter is going to be 20. So when we put up fencing or something going around, we're talking about perimeter. So let's go ahead and make ourselves a little note of that as well. Fencing goes around perimeter. And we could use whatever variables we want here. X and Y are great, okay? We just got to pick them and be consistent throughout the problem, okay? Let's talk about setting up an equation now. So remember that the thing that I am optimizing is area. So if I need to start with an equation for area, the area would simply be X times Y. Okay, so A for area, and the area of that rectangle is X times Y. The problem is right now, though, I have two variables. I've got X and I have Y. I want to somehow eliminate that to only one variable. What auxiliary equation could I use to help me eliminate one of those variables? Any ideas? Okay, now CJ, when you say y equals 20 minus 2x, what did you use to come up with that equation? Did you jump to that right away, or did you start somewhere else? Okay, so CJ, if you look at what Stephen just typed, is that where you started from? Awesome. Good, good, good. Yeah, so remember, we have this auxiliary function that we can write about perimeter, okay? So we know that the perimeter in this case would be 2x plus y, but we know that our perimeter, based on the information they gave me, ooh, that eraser was way too big for what I was erasing, is 20, okay? Does it matter which variable I solve that equation for? Whether I solve it for x or whether I solve it for y? Yeah, it really doesn't matter. Again, we just got to pick one, stick with it, and be consistent. But it's probably going to be easiest to solve for y in this case because we can just simply subtract that 2x. So, whoopsie daisy, 20 minus 2x equals y. So we're going to use this auxiliary equation we just came up with to plug into our area equation. It's the area equation that we want to optimize. So now we have area equals x times 20 minus 2x. okay? Let's distribute. Now, here's the thing. We need to take the derivative of area because we're trying to find the maximum area. We technically could do product rule, x times 20 minus 2x, but if we simply distribute here, we're going to be able to do 2 quick one steps, which will be easier. And remember, time is what you want more of on this exam. So anything you can do to make it easier for you, the better. So we're going to have 20x minus 2x squared. Okay, so now we've got to take that derivative because we're looking for the critical points. What's the derivative of 20x minus 2x squared going to give us? $20 minus 4x sounds good to me. You guys are all on a roll today. All right, now to find my critical points, remember I have to set my derivative equal to 0, and I have to figure out where my derivative does not exist. We're kind of off the hook on that second part because since this is just a polynomial, it exists everywhere. So really what we're looking at is setting 20 minus 4x equal to 0. So we'll subtract 20 from both sides. Divide by -4, and we get that x equals 5. Okay. And let's make a little note here to never D&E. So you want to keep in mind that as you look for critical points, you are looking for where the derivative does not exist and where the derivative is 0. In this case, we're only really worried about where the derivative is equal to 0, though. All right, so we've got that x equals 5. The biggest mistake I see a lot of students make is they don't answer the question. They're like, yes, I did it. X equals 5. I'm done. The question itself, though, asks me to find the dimensions. So if I need to find the dimensions of the Playyard, I not only need an x, but I need my y. Okay, so keep that in mind. Okay, let's make a number line for this. Okay, this number line is the derivative of area, so I'm going to label it as A prime just so I got everything nice and clear on my paper. Because we're talking about dimensions, the smallest dimension I can have would be just above 0, so that's really my end point. And we just solved that we could have a critical point at x equals 5. I'm going to label that as z for 0. Okay. And now we just need to confirm here that this is actually the x value that's going to give me my maximum. As long as this is my x value that's going to give me my maximum, when I test values in each of these intervals on my number line, I should find that there is a maximum at x equals 5. So let's test some values. If I were to plug in 1 between 0 and 5, and remember, I'm plugging in 1 to my derivative A prime, okay? So 20 minus 4 times 1 would give me a positive. And keep in mind, I don't necessarily care what the number is. I just care whether it's positive or whether it's negative. Okay, let's plug in a number greater than 5, say 6. Okay, 20 minus 4 times 6 would give me a positive or a negative. Okay, so Stephen, I just saw your question pop up. Would the max domain be 10 or 20? Yeah, so if we, well, okay, so because we only have 20 meters of fencing available to us, yeah, one of our dimensions couldn't be more than 20. So you're absolutely right, Stephen. Let's add that to our line there. Okay. And Sherilyn, you're right on track too. This is going to be a negative. So this confirms to me that my maximum happens when x equals 5 because my derivative changes from positive to negative, or my function changes from increasing to decreasing. All right, so we know that there is a max at 5. How do I find the other dimension now that I've confirmed that that's where the maximum is? So think about that. If I know that my maximum happens at an x value of 5, yeah, I need to plug that x equals 5 into my y equation. Okay, so let's make a little note here. We know that the max happens at x equals 5. So plug back into, now remember, if we're trying to solve for y, we want to plug into the equation that says y equals. And my y equals equation is right here above it, that 20 minus 2x. So we're going to have y equals 20 minus 2 times 5, which would be 10. So my dimensions that would maximize the area of my play yard would be 10 meters by 5 meters. That's what I'm looking at for my final answer. And notice that I went ahead and added those units as well because we're talking about the context of this problem. Can y'all see that 10 behind the video of me? Or does that not show up on your end? Yeah, okay, let me move it. That's how it shows up on my end too. So let's move that out of that corner there. So we would have x equals 5, y equals 10. So we're looking at 10 meters by 5 meters. Boom. Could they be listed interchangeably? Okay, so Sherilyn, generally speaking, when you list dimensions, in this kind of scenario, we list the larger dimension first. But as long as you're clear about which variable is which, you would be completely fine. What other questions do you have on this problem? All right, let's try the next one then. All right, the next example says, find the point on the line y equals 5x plus 2 that is closest to the origin. Okay. So let's think about what's happening here. I've got a point that's on the line, y equals 5x plus 2. And I want to find the point on that line that's closest to the origin. So what is it that I'm optimizing here? Or let me ask you this. What would be, yeah, exactly, CJ. So we're minimizing the distance. And the key here is that it says closest. So when we talk about closest, we're talking about distance. So we are optimizing distance. And you're also correct that because it's closest, we want to find the minimum. So when we make our number line with our critical points on it, we want to confirm that we are looking for the minimum. Okay. So we have a point on the line y equals 5x plus 2. Let's draw this graph out. So this is in my standard y equals mx plus b. So I have a y-intercept of 2. And I have a slope of 5. So we could go up 5, 1, 2, 3, 4, 5 over 1. And play connect the dots. Okay. And we're trying to find the closest point on that line to the origin. Now keep in mind our origin we're looking at is 0, 0. Okay. Now, this point that we're looking for, since we don't know what the point actually is yet, what way might we want to label that point as? How do we write a point? XY, perfect. So we've got some point on that line, XY, an ordered pair. We want it to be closest to the origin, which we know is 0, 0, and we are minimizing distance. So good job breaking that problem down. All right, anybody remember the distance formula? Might be a little tricky to type out. We've got that the distance formula is the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. Good job, Stephen. Okay. I'm trying to optimize distance, so that means I need to take the derivative of distance. But before I do that, I want to get that d equals equation, my distance equation, down to a single variable, okay? Any thoughts on how I might get that distance equation down to a single variable? Yeah, they actually give it to me this time, right? In the previous example, we had to come up with that auxiliary equation for perimeter, but this time they straight up give me that equation as y equals 5x plus 2. Now, there's one other piece of information we want to use. What's the other piece? 0, 0, exactly. So we're going to end up with the following. We're going to have x minus 0 squared plus y minus 0 squared. But now we know that y is simply 5x plus 2. Okay. As we continue to go through these examples, I've used this phrase, but I guess I haven't really explained it. An equation like y equals 5x plus 2, I often call an auxiliary equation or secondary equation. And then that one that we're actually trying to optimize is going to be our primary equation. Okay, so when I say that word auxiliary equation, we're kind of saying, what's that extra piece I need to eliminate one of those variables? All right, we've got our distance formula. It is all in terms of x right now. So let's take the derivative, okay? What rule should we use to take the derivative? Would it be smart to add and multiply everything first and use the power rule? Yes, I agree. So we are going to use the chain rule. And you totally read my mind, Stephen, because my next question for you was going to be, is there anything else we could do to make it a little bit easier for ourselves? So yeah, if we go ahead and expand 5x plus 2 and combine some like terms, when we use that power rule, it's going to be easier to take the derivative of the inside. Okay, so let's go ahead and do that now. So this would be the square root of x squared plus. Now keep in mind, when I square the quantity 5x plus 2, this really means 5x plus 2 times the quantity 5x plus 2. Okay, good old algebra there. Sometimes I have some students that make the mistake of saying, oh, it's just 25x squared plus 4. But you just missed all the middle terms. Okay, so we are really going to get 25x squared. My outer and my inner are both going to give me 10x, so that's going to give me a 20x. And then my last term is going to give me 4. Yeah, so now when we go to combine those, that 25x squared and my x squared is going to give me a 26x squared. Double check that 10x. When you do your outer and your inner, you're going to get a 10x and then another 10x. So we should get a 20x there. Yep, it happens. You just got to be careful. All right, so we've got 25x squared plus 20x plus 4. All right. Now, keep in mind, we're still just cleaning up and rewriting that initial distance formula that we're going to optimize. Now that we've cleaned it up a little bit, it's going to be much easier for us to use that chain rule now. Square root is the same as an exponent of 1/2. So this is really 26x squared plus 20x plus 4 to the 1/2. Now let's take the derivative. So we are going to get that the derivative of my distance is equal to the derivative of the outside function. So we're going to have 1/2 times something to the negative 1/2. I'm going to copy the inside, which gives me 26x squared plus 20x plus 4. And now I'm going to multiply this by the derivative of the inside, which should give me a 52x plus 20. Okay, we've got our derivative. Let's make it a little bit easier to use, because if we're thinking ahead to finding our critical points, we need to find out where my derivative equals 0 and where my derivative does not exist. Okay, when we clean this up, I always have my students get rid of the negative exponent. So remember, to rewrite that negative exponent in the denominator, that exponent is going to become positive. So this derivative is going to be equal to 52x plus 20 over 2 times 26x squared plus 20x plus 4 to the positive 1/2. Now, at this point, if you wanted to rewrite that exponent of 1/2 as a square root, it's equivalent. You could. We've got our derivative. Now we need to find our critical points. So we need to figure out when this derivative equals 0 and when this derivative does not exist. Take a couple minutes on your own paper and see if you can figure out where this derivative equals 0 and where this derivative does not exist so you can find those critical points. So could you simplify that x value, Stephen? Yeah, good, good, good. Sherilyn, did you get the same answer too? Okay, awesome. Not a problem, Sherilyn. Stephen, on the free response section, you do not need to. However, if it were a multiple choice question and you didn't see the option of -20/52, you'd of course want to look to see what you would get if you would simplify that and then look for that option. So, kind of depends on where that problem comes up. You just gotta be aware of that. Why did the derivative always exist? Okay, yeah. So, Stephen, on my paper, when I did out this problem, I actually went through the process of setting 2 times 26x squared plus 20x plus 4 all to the 1/2 equals 0. Because when I'm looking, I just wrote where y'all can't see again, sorry. When I'm looking for where that derivative doesn't exist, I'm looking to make sure that my denominator doesn't equal 0. But you're right, if I try to solve that, I'm going to find out that my denominator never equals 0. So in this case, my derivative is always going to exist. Okay. CJ and Sherilyn, you on board with that too? Awesome. Good, good, good. Okay. So we just found out that we have on our number line a critical point at -5/13. Okay. What would be my endpoint on this number line? So here's the thing. To be honest with you, when we look at this number line, if we didn't think about what I'm about to say, it would not be the end of the world because we could still confirm that this is a minimum. But can you ever have a distance that's negative? No. So really, the lowest distance we could have would be 0. Okay. Let's plug in something between 0 and -5/13. So what do you want to plug in? Any ideas on what number we might want to test in this interval? Because I'm losing my mind, Stephen and CJ. That's why. That is why. Okay, for my own sanity, okay, it's Saturday, cut me a little slack, but not too much, okay? This value we have found is an x value, right? So we're talking about coordinates on a point xy, right? My x value of my coordinate absolutely can be negative. Okay, so are we back on the same page now? I was so focused on that distance that I was thinking distance can be negative, but this number that is on my number line is an x coordinate. Okay, let's plug in -1. How's that sound? And on the other side, maybe we want to actually plug in 0. If I plug -1 into my derivative, do I get a positive or a negative? Awesome. And if I plug in 0, I get a positive. Good. So we are finding at this point that we have confirmed that my minimum happens at an x value of -5/13. Okay, and we know that's a minimum because my derivative's changing from negative to positive, or my function's changing from decreasing to increasing. Okay, we have to answer the question though. It wants me to find the point. Right now I have only found my x value. I've got to go back to my auxiliary equation and plug it back in to figure out my y. Yep, exactly, Sherilyn. Can our x value be plugged back into the original equation? When you say the original equation, do you mean the y equals 5x plus 2, Sherilyn? Yes, perfect, exactly. So because we're trying to find y equals, we want to plug into the equation that says y equals. So we're going to have 5 times -5/13 plus 2. So what do we get? -25/13 plus 2, which is really -25/13 plus 26/13, which would equal 1/13. Good, good, good. So the point that is on the line y equals 5x plus 2 that is closest to the origin is the point -5/13, comma 1/13. All right, looks like we got time for one more. We have a box with a square base and open top that must have a volume of 4,000 cubic centimeters. Find the dimension of the box that minimizes the amount of material used. So our box has a square base, so that means my length and width are going to be the same. We've got an open top, so we have a bottom and 4 sides, but no top. That volume has to be 4,000 cubic centimeters, and we are trying to find the dimensions of the box that minimize the amount of material being used. What is it that I am optimizing in this problem? So CJ and Steven, I really agree with both of you. Oh, wait, CJ. Okay, be careful, CJ. Where you say to maximize the volume, no, you're good. No need to apologize. If we're trying to minimize the amount of material used, okay, when we go to write an equation for the amount of material used, because that's what we're trying to minimize, that's what we're trying to optimize, it's really the surface area that we're talking about when we talk about the amount of material. So we are optimizing surface area. Okay, and in optimizing that, the best in this case is that we want to use the least amount of material. Okay, so we're going to minimize that surface area. All right, let's draw ourselves a nice little box here. Okay, and keep in mind that this is a square base. So my length and my width here are the same. I'm going to call both of them X. And my height, I'm going to go ahead and call Y. Okay, so we need to write an equation for surface area because that's what I'm optimizing. Remember that surface area is really just the area of all the sides added together. So keep in mind we have a base. The area of that base would be x times x, which is x squared. We don't have a top, so we don't have to worry about that. And we have 4 sides. All 4 of these sides have the same area, and the area of each side would be x times y, so we have 4xy. That would be the equation of my surface area, x squared plus 4xy. Small problem, got 2 variables. Now we can use that volume you're wanting to use. We've got to write an auxiliary equation to eliminate one of those variables. We know that the volume equals 4,000 cubic centimeters. So we know that volume equals x squared times y, which equals 4,000. So from that, we could get that y equals 4,000 over x squared. So that's my auxiliary equation that now I'm going to plug into my primary. So we have that the surface area equals x squared plus 4 times x times 4,000 over x squared. And now we can do a little simplifying here. 4 times 4,000 is going to give me 16,000, and x over x squared is going to give me an x in the denominator. All right, we need to take this derivative. What rule should I use to take this derivative? Oh, hey, Robert. We got a new person. Awesome. Thanks for joining us, Robert. We could use the quotient rule, Robert and Sherilyn. I personally would be inclined to do a little something to the surface area equation first so that I could use one steps and not have to do the quotient rule. What could I rewrite that 16,000 over x squared as? Yeah, if I move that x squared to the top, I'm going to have an x to the negative 2, and then my 2 little one steps are just power rules. You are not going to get the wrong answer if you use the quotient rule, but in my opinion, it's a little bit easier and more efficient to use that power rule. So if we rewrite this as x squared plus 16,000 x to the negative 2, I'm going to find when I go to take my derivative, that we get 2x minus 32,000 x to the negative 3. questions? Okay, I need to figure out when this derivative equals 0 and when this derivative does not exist. In doing so, in my opinion, it's going to be a little bit easier if I now manipulate this derivative a little bit and get rid of that negative exponent and give myself a single fraction. Okay, so we could rewrite this derivative as 2x minus 32,000 over x cubed. Hey y'all, there's an error here, and y'all didn't call me out on it. Anybody see the mistake I made? Exactly, Stephen. Gosh, I'm not with it today. Okay, back here, when I look at 4x times 4,000 over x squared, I think I said it correctly, but I didn't write it correctly. It should be 16,000 over x. I'm going to get my head on straight. So when I rewrite this for the power rule, I'm going to have x to the negative 1. Let's erase the rest. Fresh start. I'm going to have that the derivative of my surface area equals 2x minus 16,000 x to the negative 2. Does that look better? And if we rewrite this, we're going to get 2x minus 16,000 over x squared. Now, when I want to figure out if this derivative equals 0 or ever doesn't exist, it might help me to go ahead and condense this down to a single fraction as well. And let's get that common denominator x squared, which would give me 2x cubed minus 16,000 over x squared. All right, where does my derivative equal 0 and where does my derivative not exist? Where are my critical numbers? Yeah, so I'm going to find that the numerator equaled 0 when x was 20. And at 0, my denominator equals 0. So at 0, I have a D and E. All right, let's plug in some numbers. Maybe 1 between 0 and 20. And we should find that we get a negative. Any number greater than 20, what do you want to plug in? 25. Sounds great, Robert. If I plug in 25 into my surface area derivative, do I get a positive or a negative? Awesome. Positive. Okay. And again, here I'm just confirming for myself that this indeed is a minimum. Because remember, I'm trying to find the minimum surface area, the minimum amount of material used. So my surface area derivative has changed from negative to positive. So I know that that's a minimum. All right, answer the question, ATQ. If I have a minimum at x equals 20, to answer this question, I have to find the dimensions. I still need my y value. But lucky for us, we have already written an equation right above that says y equals 4,000 over x squared. So we are plugging in to get that y value. And what's 4,000 over 20 squared going to give me? 10. Rock on. So going back to your previous question, Sherilyn, when I write this answer, you're going to see that I actually write this as 20 centimeters by 10 centimeters. And that's just a notation thing in terms of how dimensions are traditionally listed. Now, if I'm looking at the dimensions of the box, right, really this 20 is my x value. And how many dimensions does this box have? Is a box 2D or 3D? It's 3D, right? So even though my measurements are the same for my length and my width, and we found that they were both 20, we really should have 20 by 20 by 10. Let me erase that and then squeeze it back in there. 20 by 20 by 10. Questions? Any questions in general about optimization? No. The biggest advice I can give you when it comes to optimization is really reading the question and deciding up front what it is that you're optimizing. Look for that keyword in your problem, that maximizing, minimum, fastest, closest, shortest, furthest, and then see what it's followed by to see what it is that you're optimizing. So like in this one, we knew we were optimizing the amount of material, and that amount of material translates into surface area, okay? Could you also write 20 squared centimeters by 10 centimeters for the square base questions? So I think because you're asking me because it's the same dimension, is that why you're saying that, Robert? Yeah. So really, because it's 3 dimensions, in my opinion, all 3 dimensions should be listed out. If you wrote 20 centimeters by 10 centimeters, since that one dimension does repeat, it would be understood what you meant. But I like to not leave any confusion out there. And if there's 3 dimensions, list all 3, even if it repeats. What else? Any other questions? No? Okay. Well, I hope that the general process we outlined and the couple examples we were able to do today helped you better understand that optimization process. I'm so proud of you guys and impressed that you came out on a Saturday afternoon to do some calculus. I mean, what could be more fun, right? I love calculus, so should you. And thanks for bearing with me in my few couple mental lapses there. I appreciate you guys. You're very welcome, Sherilyn. And I hope to see you guys again in a future stream. It was great having you guys, and I really appreciate how engaged and active you were as well. Have a wonderful Saturday and enjoy the rest of your weekend. Have a great time. Bye.